Hello students, welcome to aimsindia online classes. This is a chemist session. Here we are discussing about the chapter structure of the atom. In this session we are going to say about a new concept, that is electromagnetic radiation. In the earlier sessions we have seen about different subatomic particles, their existence and discovery, their properties and electronic configurations, and different atomic models also have seen. Now we are going to say a new concept called electromagnetic radiation. Electromagnetic radiation, simply it is called EMR. This electromagnetic radiation is a form of energy that is produced by the moment of or oscillation of electrically charged particles like electrons, which are traveling through vacuum or matter. Okay, the energy produced by the electrically charged particles which are continuously moving, that energy emitted is called electromagnetic radiation. Okay, so these radiations do not need any medium for their propagation. They can move through matter as well as through vacuum also. That's why we say these electromagnetic radiations do not need any medium for their propagation. See, these all are different examples for the electromagnetic radiations, like visible light, ultraviolet radiation, infrared radiation, X-rays, gamma rays. These all will come under different kinds of electromagnetic radiations. These all are the different forms of energy which are produced by the moving electrically charged particles. Okay. Now let us see what are the characteristics of these electromagnetic radiations. Electromagnetic radiation is released as photons. Photon in the sense small packets of energy, which are bundles of energy, light energy that travel at a speed of light. So these electromagnetic radiations are released in the form of small packets or small bundles of energy, which are called as photons. These photons are being traveling with the velocity of light. We know the velocity of light is equal to 3 into 10 to the power of 8 meters per second. These all electromagnetic radiations are supposed to travel with the same speed. So electromagnetic radiation can travel through empty space, that is through vacuum also. But most of the other types of waves must travel through some sort of the substance. So for the traveling of other types of waves, there should be some sort of substances. For example, sound waves need either a gas, solid, or liquid to pass through in order to be heard. So in the presence of a certain medium only, the sound can travel. Sound waves can travel. But for this traveling of electromagnetic radiations, no medium is needed. They can travel through the medium, or without medium, even through vacuum also they can travel. So an electromagnetic radiation is always characterized by certain properties. Let us see what are those properties which are characterizing an electromagnetic radiation. So the first one, wavelength. The distance between the two nearest crests or nearest troughs of an electromagnetic radiation or wave is called its wavelength. It is denoted by the symbol lambda. It is pronounced as lambda. It is a symbol for wavelength. It is pronounced as lambda. And it is measured in terms of centimeters, angstroms, micrometers, or nanometers. Because we are telling this is the distance between the two adjacent troughs or crests of a wave. So as it is being a distance, it is measured in terms of angstroms, micrometers, nanometers, centimeters, even you can use meters and these all. But it is being very micro quantities. They will be generally calculated in terms of angstroms, micrometers and nanometers. Suppose this is a wave. It is passing like this. Now the distance between the two adjacent crusts, or the distance between the two adjacent troughs. So if you take these two crests, these two are adjacent, the distance between these two crests is termed as now wavelength. The distance between the two nearest crests is denoted as wavelength. It is also defined as the distance between the two adjacent troughs. Suppose for this wave, these two are adjacent troughs. The distance between these two is also considered as wavelength. So if you say one complete wavelength, it represents a crest and a trough. So this is a complete wave. This distance is called wavelength. It is denoted with the symbol lambda. We know 1 angstrom is equal to 10 to the power of minus 8 centimeters or 10 to the power of minus 10 meters. And even 1 micrometer is equal to 10 to the power of minus 4 centimeters. And even 1 nanometer is equal to 10 to the power of minus 7 centimeters. By using these unit conversions, we can do calculations based upon the wavelength. Okay. Next property or next characteristic is frequency. It is defined as the number of waves which pass through a point in 1 second. Or simply to say, the number of waves passing through a point per second is defined as frequency of that radiation. It is denoted the symbol nu. So this is a symbol for frequency. It is pronounced as nu, and it is measured in terms of cycles per second or hertz, because we are telling it is number of waves passing through a point per second, number of waves per second. So you say cycles per second or oscillations per second or hertz. These all will be considered as units for frequency. And here frequency is inversely proportional to wavelength. Yes, if the wave, if it is having greater wavelength, then the number of waves passing through a point per second will be less. That means frequency is less. And if a wave it is having wavelength very less wavelength, then the number of waves passing through a point per second will be greater. That means frequency will be greater. In that way, frequency is inversely proportional to wavelength. If one is greater, the other one is smaller. So we can mathematically represent this relation as nu is directly proportional to 1 by lambda, or we can also denote this as nu is directly proportional to 1 by lambda, or nu is inversely proportional to lambda, we can pronounce it. To remove the proportionality, here a constant is taken which is called as velocity of light. So we can say nu is equal to c by lambda. This is the relation between wavelength and frequency of an electromagnetic radiation, where c is a constant which is equal to velocity of light. What is the velocity of light? 3 into 10 to the power of 8 meters per second. That is velocity of light. Thus, a wave of higher frequency has a shorter wavelength, while a wave of lower frequency has a longer wavelength. Okay, from this we say frequency is inversely proportional to wavelength. If we consider two waves like this, suppose a wave is having wavelength this much, and one more wave is there with this much frequency. Now, if we give a point in the path of these two waves, the number of waves passing through this point per second for this wave will be less, isn't it? If you consider for this wave, number of waves passing through this point per second will be greater. So for this wavelength is greater, then frequency is being smaller because bigger wavelength. And if you see for this wave, wavelength is smaller, so frequency is being greater. So from this we can say frequency is inversely proportional to wavelength. Next, longer wavelength waves such as radio waves carry low energy. So here we told the longer wavelength waves will be having lower frequency. If frequency is less, energy also will be less for them. This is why we can listen to the radio without any harmful consequences. isn't it? We can continuously listen the radio without any harmful consequences, because the waves emitted by the radio, that we call radio waves, they have very longer wavelength, so they will be having less energy and cause no harm to us. But shorter wavelength waves such as X-rays carry higher energy that can be hazardous to our health. That is why uh, lead aprons are worn to protect our bodies from harmful radiations when we undergo X-rays. Okay, so certain radiations which are having shorter wavelength, just like X-rays. If the wavelength is shorter, frequency will be very high. If the frequency is high, then energy also will be high for them. So if energy is higher, they may cause harm to us. That's why you say they can be hazardous to our body or our health. That's why generally the people who are exposed to X-rays will be wearing these lead aprons to protect their bodies from these harmful radiations. Okay, see here the relation we can find. This is a wave with a shorter wavelength. This is the wave with a longer wavelength. If we keep a point in the path of these two waves, then if we count the number of waves passing through this point per second, this will be greater for this. Whereas if we count for this wavelength, for this wave, the number of waves passing through a point per this point per second will be less because greater wavelength. In that way, frequency and wavelength are inversely proportional. If higher is the frequency, shorter is the wavelength, and vice versa. Okay? Frequency and wavelengths of different electromagnetic radiations are represented here. See, different electromagnetic radiations are shown. So, radio waves, microwaves, infrared rays, visible radiation, ultraviolet radiation, X-rays, gamma rays. If you observe there, frequencies and wavelengths. See here, the wavelength is mentioned in terms of meters. Radio waves are having greater wavelength, 10 to the power of 3 meters wavelength. Whereas if you see gamma rays, 10 to the power of minus 12 meters, very shorter wavelength. So if you observe their frequencies, frequency is much higher for radio waves, and it is very smaller for radio waves, and frequency is much greater for gamma rays. Okay, now let us see another property, wave number. This is a reciprocal of wavelength, that is the number of wavelengths per u centimeter. The number of wavelengths per centimeter is defined as wave number. Simply to define this as, it can be defined as the reciprocal of wavelength. So it is denoted with the symbol nu bar. This is a symbol for nu bar, and it is pronounced as nu bar. Nu is a frequency, nu is a symbol for frequency, but nu bar is a symbol for wave number. It is expressed in centimeter inverse or meter inverse. Okay. Now the relation between the wavelength and frequency can be represented like this. Nu bar is equal to 1 by lambda because it is reciprocal to wavelength. Okay, it is one property. Next property, amplitude. It is defined as the height of the crest or the depth of the trough of a wave. It is denoted by the letter A. Okay, amplitude is denoted with the symbol A, and it is defined as the height of a crest or depth of a trough. It determines the intensity of the radiation. See, suppose this is a wave. The height of this crest is taken as a amplitude of this wave or the depth of the trough. So this also will be taken as the amplitude of this wave. As amplitude increases, its intensity of that radiation increases, and it is denoted with symbol small a. Okay, it is one character. Let us see one more character, that is velocity of electromagnetic radiations. It is defined as the distance covered in 1 second by the wave. It is denoted by the letter c. Okay, the distance covered in 1 second by the wave is defined as velocity of that electromagnetic radiation. All the electromagnetic waves or all the electromagnetic radiations, they travel with the same velocity, that is equal to velocity of light. The quantity of that velocity of light is 3 into 10 to the power of 10 centimeters per second, or 3 into 10 to the power of 8 meters per second. This is the velocity of electromagnetic radiations. The distance traveled in 1 second is equal to c is equal to lambda into frequency, that is equal to 3 into 10 to the power of 10 centimeters. How it is derived? Earlier we have seen the relation between the frequency and wavelength. We told frequency is inversely proportional to wavelength. So it is represented like this mathematically. Frequency is inversely proportional to wavelength. To remove this proportionality, we told a constant is used, that is equal to velocity of light. So this is the relation between the frequency, velocity of light and wavelength. So here we want to calculate the of the velocity of the light. C is equal to, what will be happen if you cross multiply these two, we get C is equal to nu into lambda. Okay. Next, time period. The time taken by the wave for one complete cycle or vibration is called time period. So the time taken by a wave or electromagnetic radiation to complete one complete wave or one complete cycle is called its time period. So this time period is denoted with the symbol T. Its units will be seconds per cycle, means the time taken for the one complete cycle or one complete oscillation or one complete vibration, that is called time period. Suppose a wave is traveling like this. Now if we keep a point here, the time taken by this wave for the complete wave passing. So suppose from this point if it is started, for this wave, for complete the time taken for the complete wave passing through that point is considered as time period. It is denoted with the symbol T. Okay, its units will be seconds per cycle. Okay, here it is mentioned C. It's amplitude and it is time period. Time taken by this wave to pass for the complete one wave. So from here to here, the time taken is called time period. Okay. The arrangement of various types of electromagnetic radiations in the order of their increasing or decreasing order of wavelengths or frequencies is known as electromagnetic spectrum. That means when all the with different types of electromagnetic radiations, if they are arranged one by one in the either increasing or decreasing order of their wavelengths or frequencies, then that arrangement is known as electromagnetic spectrum. We know certain wavelengths. Let us see that electromagnetic spectrum diagram here. See, all the types of electromagnetic radiations are arranged here. Radio waves, microwaves, and infrared light radiation, visible light, ultraviolet radiation, X-rays, gamma rays. These all are different types of electromagnetic radiations. And if you observe, these all are arranged in the decreasing order of their wavelengths. Say for the radio waves, wavelength is much greater, and for the gamma rays, wavelength is very shorter. If you see in terms of frequency, they are arranged in the increasing order of their frequency. Radio waves are having very shorter frequency, very lower frequencies. That's why you say these radio waves having less energy and they are not harmful. So we don't get any harm even by listening to the radio, because the radio waves are having greater frequency or very low energy. Whereas if you see these X-rays and gamma rays, these are having shorter wavelength. At the same time, they have greater frequency. If the frequency is greater, their energy also will be much greater. If the energy is greater, there will be very harmful radiations. That's why we should not be exposed to these X-rays and gamma rays. They may cause harm to our body. That's why only the people who are continuously being exposed to these X-rays and gamma rays, they wear certain specially designed aprons that we call lead aprons to protect from these harmful radiations like X-rays and gamma rays. See here at the middle there is a visible radiation. This is the only light which we can see, a certain frequency. Okay, the light which is visible to naked eye is called visible light, and the radiation is called visible radiation. Remaining radiations we cannot see with our naked eye. That's why we can see the reflection given by the X-rays on the bones, but we cannot see those X-rays. Of course, they are very harmful. Okay, this is about electromagnetic radiations. Electromagnetic radiations means the radiations emitted by the particles which are moving with a very high velocity and having charge, just like the electrons. Even electrons, while revolving with the high velocity, while jumping from one orbit to another orbit, they emit certain radiation. For suppose certain electrons from the higher orbits they jump into lower orbits. They emit certain energy in the form of this electromagnetic radiation. That radiation emitted by these electrons will possess these all properties which we discussed till now, like the wavelength, frequency, amplitude, time period, velocity, and this all. Okay. Thank you for watching our video. Please subscribe our YouTube channel Aims Today and visit our website aimstoday.in for latest updates on recorded videos.